Hi guys, welcome back. This is lecture 30. Today we will be talking about things having to do with chemical equations. Specifically, we're going to be talking about percent yields and limiting reactants. And I'll detail what those are in a sec, but we're going to start out with limiting reactants. I'm going to use a few food metaphors and references to explain this. But when we cook food, let's say we're cooking some chocolate chip cookies, we look at a recipe right here. And we read the ingredients off of that recipe. Now, a chemical equation is very similar to a recipe in that it tells us the amounts of each species that we need to put in. But let's say that we're making some cookies, and we start out with a big bag of flour, so we have tons of it, but we are only starting with 4 eggs. Now, which is going to control the amount of cookies we're going to make? Is it going to be this big bag of flour or just these 4 eggs? It's going to be the 4 eggs, right? They're going to control how much cookies we can make, and then we're just going to have a bunch of leftover flour. Well, a limiting reactant is exactly the same as this. It limits your reaction. It limits how much you can make. So it limits how much product you can make, and we generally consider or assume that it's completely used up during the reaction. Now, that would be the eggs in this analogy. And then what would the flour be? The flour would be what we call the excess reactant or reactants. So anything that we have extra of is excess. It doesn't control how much product we can form, and it's not completely used up. So there's always some left over at the end. So let's look at this problem right here, where we have 2 moles of hydrogen gas reacting with 1 mole of oxygen gas to form 2 moles of water gas. Now this first part, the reactants, is illustrated here in this box where we have the water or the oxygen molecules represented by these red molecules. We have the hydrogen molecules represented by the white molecules. The question we want to ask then is, which one is going to run out first? Well, to address this problem, the first thing we need to know is how much of each is there. So let's count the oxygen. There is 1, 2, 3, 4, 5, 6 oxygen molecules, and then there are 1, 2, 3, 4, 5, 6 hydrogen molecules. So there's the same number of each. Does that mean they're going to run out at the same time? No. Why not? Because it takes 2 hydrogen molecules to react with every 1 oxygen molecule. Another way of looking at this is for this hydrogen molecule, it has 2 hydrogen atoms, and to make water, both of these hydrogen atoms are going to have to bond to a single oxygen atom. So when this thing is completely reacted, we're going to end up with 1, 2, 3, 4, 5, 6 water molecules, but there's also going to be 1, 2, 3 oxygen molecules left over. So which one is going to be used up first? It's going to be hydrogen, because it takes more moles of hydrogen to get this reaction to go forward. All right? So we're going to have to figure out how to determine which species is our limiting reactant. We're going to go over several ways of doing that. Okay, so let's say we're starting with this reaction right here. We have 3 moles of magnesium plus 1 mole of N2, and that is going to form 1 mole of magnesium 3 nitrogen 2. Let's say we start with 35 grams of magnesium and 15 grams of nitrogen gas. And we want to ask how many grams of Mg3N2 can we form from that? Well, the first thing we can do is try and figure out the number of moles, or sorry, the number of grams of this that can be formed with 35 grams of magnesium, and figure out how much could be formed with 15 grams of nitrogen. What I mean by that is we're going to calculate the amount of product possible from each reactant. And the one that produces less magnesium 3 N2 is going to be our limiting reactant. So let's start with magnesium. We have 35 grams of magnesium. We need to turn that into moles. That's always what we're going to do first. We're going to take 35 grams of magnesium divided by 24.3 grams of magnesium per mole of magnesium. Now we have that in moles. We're going to multiply that by our mole fraction between magnesium 3 nitrogen 2 and magnesium. So Mg3N2 has 1 here. The magnesium has a 3, so we're going to multiply by 1 divided by 3. And that gets us now into moles of magnesium 3 nitrogen 2. Then we're going to have to figure out how many grams come from that, so we're going to multiply by the molecular weight of the Mg3N2, which is 100.9 grams per mole. And that gives us a total of 48 grams of Mg3N2 if we're starting with 35 grams of magnesium and assume we have unlimited nitrogen. Now let's do the reverse. Let's calculate with nitrogen. We're going to say we have 15 grams of N2 and pretend we have unlimited magnesium. Figure out how many moles of Mg3N2 we can make. Well, we're starting with 15 grams of nitrogen. We need to divide by the molecular weight of nitrogen, then multiply by the mole ratio between the magnesium 3 nitrogen 2 and nitrogen. That is a 1:1 ratio. And then, of course, again, we're going to multiply by the molecular weight of our Mg3N2. And that is going to give us a total of 54 grams of Mg3N2. Now, if you look at this, what this means is with 35 grams of magnesium and 15 grams of nitrogen, the magnesium is producing less than the nitrogen. Now, in reality, we're not producing the Mg3N2 from just one species or the other. We're using both. And so one of these is going to get completely used up. When it's used up, the reaction stops. And that means that it's going to stop after we produce 48 grams of Mg3N2. There's not enough magnesium to make 54 grams of Mg3N2. There might be enough nitrogen. There's not enough magnesium. So our limiting reactant then is magnesium, and we can produce just 48 grams of the Mg3N2. Okay, but the question is there a little bit shorter process for finding the limiting reactant? There is. In this case, what we're going to do is just stop at the number of moles of product that we're forming, not figure out the number of grams. And the reason we would want to do this might become obvious to you in a second. It saves us just a little bit of work. So if we start with the magnesium again, we figure out how many moles of magnesium we have and then multiply it by the mole ratio between Mg3N2 and magnesium, which is 1:3. We find that we could produce 0.48 moles of Mg3N2. If we do the same thing with the N2, the 15 grams of N2, divide by its molecular weight, and multiply by the mole fraction, we find that we could produce 0.54 moles of Mg3N2. Now we know that our magnesium is our limiting reagent because we can make less of it. And then we can just multiply this one by our molecular weight of Mg3N2 to figure out what we're actually supposed to get. That way you don't have to calculate how many grams for each of them, and it just saves this one little step for your excess reagents. Is there an even shorter process to do this? I don't think so. Some people think this is a shorter process. To me, it seems like the exact same amount of work as the last way of calculating this. This one, we're going to stop at the moles of reactants and compare them using the mole ratios in our balanced equation. So what that means is we're going to calculate the number of moles of magnesium present. So we're going to take that 35 grams of magnesium, divide by 24.3 grams of magnesium per mole, and find that we have 1.44 moles of magnesium. Then we're going to take our nitrogen, figure out how many moles of that. So we're going to start with our 15 grams of nitrogen, divide by the molecular weight of nitrogen, and find that we have 0.54 moles of nitrogen. So now that we know how many moles of each we have, we can compare to the ratios we should see in this formula. So the stoichiometric ratio of nitrogen to magnesium up here in our equation is 1 to 3, right? I have that written down here. N2 to magnesium is 1 to 3. But what we've calculated is that we have 0.54 to 1.44. That's not super easy to compare to 1 to 3, especially for people that aren't just great at doing math in their head. So what we need to do is turn at least one of those numbers into a whole number. The way we're going to do that is whichever of these values is less. So in this case, the 0.54 is less. So we're going to divide both of these numbers by 0.54. So that's going to be, so for 0.54 divided by 0.54, that's going to equal 1. And then 1.44 divided by 0.54 is going to be equal to 2.7. Now this is our ratio that we can compare easily to our 1 to 3 ratio. Now we see that magnesium, our actual magnesium, is slightly less than our 3 here. And so since it's slightly less, we're going to know that magnesium is our limiting reagent. Sorry if I'm going a little fast for you. This is all basically trying to calculate the same thing. We'll do a little review of it in a second. But because that guy is a little low, we know that our magnesium is our limiting reagent. So we can take our moles of magnesium, multiply by our mole fraction of Mg3N2 to magnesium, multiply by our molecular weight of the Mg3N2, figure out how many grams of Mg3N2 we have. The one last way of doing this is we can figure out how many moles of everything we have, and then we can figure out if I have this many moles of N2, how many moles of magnesium would I consume? Or if I have this many moles of magnesium, how many moles of nitrogen could I consume in this reaction? So we'll just look at the nitrogen. We have 0.54 moles of nitrogen. We're going to need to multiply that by our mole fraction between magnesium and nitrogen. And we can see that if we have 0.54 moles of nitrogen, we could also use up 1.62 moles of magnesium. Now, of course, 1.62 moles of magnesium is higher than what we actually have, which is 1.44 moles of magnesium. And since our nitrogen can use up more moles of magnesium than is present, we know, of course, that our magnesium is the limiting reagent. We can calculate how much Mg3N2 we can get out of that. So to review those 4 ways that we just covered to find our limiting reactants or limiting reagents, the first was we can calculate the grams of product possible from each reactant. So in this case, the reactant that makes the smallest amount of product is limiting. The second way of doing this is we can calculate the moles of product possible from each reactant. So this one is very similar to the first one, except we don't take it to that next step of calculating how many grams each one is going to produce. But again, in this one, the reactant that makes the fewest moles of product is limiting. The third way we talked about was to calculate the moles of each reactant and then compare the actual mole ratio that we see to the stoichiometric mole ratio in our equation. Now, this one gets a little confusing because we're going to have to divide both numbers by the smallest number of moles to get a whole mole ratio. Then we're going to have to compare the actual ratio to the mole ratio in the balanced equation, figure out which one is off, whether one of our reagents is high or low. And then the last one we tried was to calculate the moles of each reactant and use one reactant to figure out how much the other reactant is needed. Now these last two right here are most useful when you have a reaction with only two reactants, but sometimes you'll have a reaction with 3 or 4 reactants. In those cases, it's generally easier to use 1 or 2. But methods 3 and 4 are also useful for various things, as we'll get to here in a moment. Before we do that, let's go through an iCLICKER quiz. In this question, we're going to ask, how much sulfuric acid can you make if you have 20 grams of SO3 and 10 grams of water? Now we're following this reaction up here. In this one, the reaction is already balanced, but you could guess that I could give you a reaction and say balance this reaction, and then figure out which one is the limiting reagent. In this case, though, since it's balanced, what we're going to need to do first is figure out how many moles of reactants we have here. So we're going to have to take our 20 grams of SO3, turn that into moles, and we have 0.2498 moles of SO3. Now let's figure out how many moles 10 grams of water is. That is 0.5549 moles of water. Now in this equation up here, we should have 1 mole of SO3 for every 1 mole of water. But our actual ratio, as we can see, is a little off. Our actual ratio is we have 1 mole of SO3 for every 2.2 moles of water, which means that our SO3 is going to be our limiting reagent. All right, so let's calculate how many moles of H2SO4 we can produce from that. Well, we already know we have 0.2498 moles of SO3, and we can see from our equation that the mole ratio between H2SO4 and SO3 is 1 to 1. And so we have 0.2498 moles of sulfuric acid being produced. Then we're just going to have to multiply that by the molecular weight of sulfuric acid. When we carry this math through, we find that we produce 24.48 grams of sulfuric acid. If you have any questions about that, let me know. And a lot of these problems that we've been working through, oh, no, that's a different point. I'll have to make it later. My apologies. All right, so these reactions, though, that we've been talking about, they've all been a reaction with 2 reactants, but this can, or we can have the case where there's 3 reactants. A good analogy of this is making a sandwich with bread and meat and cheese. So just like if you have the wrong number of ingredients in making sandwiches, you're going to get some things left over. In chemical reactions, we often actually have leftovers as well. Now, why is this important? Let's say that you're a supplement company and you've just made a bunch of vitamin B12. Well, you had to make that out of other chemicals that aren't vitamin B12. And while your customer wants a lot of B12 in that gummy bear that they're chewing to get themselves healthy with all the sugar in it, they don't want all the ingredients used to make B12, because those ingredients are going to react very differently with your body than the vitamin B12 is. So it's often useful to know how much of our starting material is left over, how much of it can be eliminated, or how much of it we need to remove out of our reaction vessel. So now that we figured out how to figure out our limiting reagent, now we need to figure out how much of our starting materials are left over. Let's say that we're wanting to make some sulfuric acid from SO3 and water. How much sulfuric acid can you make if you have 5 grams of SO3 and 10 grams of water? And what will be left over? So the first thing we're going to have to do, of course, is figure out how many moles of SO3 and how many moles of water we have. So we'll do that really quick. And we're going to have 0.0625 moles of SO3 and 0.556 grams or moles of water. Now we can look at this equation up here and see that we should have just 1 mole of each of these, but down here in reality we have much more water than we have of SO3. So what that means is that our SO3 is our limiting reagent, and it'll be all used up. All right? So let's figure out how much H2SO4 we're making. So we're going to take 0.0625 moles of SO3 multiplied by the mole fraction between sulfuric acid and SO3 and multiplied by the molecular weight of the sulfuric acid, right? So that's stuff we're all very familiar with, hopefully by now. But how much of our water is left over? Well, to figure that out, we are going to figure out how much water is used up by the SO3. How much of the water reacted with the SO3. So we'll take this 0.0625 moles of SO3, multiply by the mole fraction between water and SO3, which in this case is 1:1, and we find that we used up 0.0625 moles of water. So that's how much was used, and we started with 0.556. Hopefully you can guess the next step, but if not, here it is. We're going to take what we started with, subtract what we used, and that's going to give our leftover amount of water. So we're left with 0.494 moles of water. Right, and then we can convert that into grams and get 8.89 grams of water. But that's how you're going to calculate how much of a excess reagent is left over. Figure out how much was used up by the reaction, subtract that from your original amount, and then you have what's left. Again, those steps: find the limiting reactant, calculate your amount used, so assume all of the limiting reagent is used up, calculate how much of the excess reagents are used, then subtract the amount of used excess reagent from the original amount of excess reagent. And there you go. You have how much is left over. Let's practice that really quickly. We're going to look at this reaction where 2 moles of aluminum are reacting with 3 moles of chlorine to give us 1 mole of aluminum 2 chlorine 6. If we start with 1 mole of aluminum and 1 mole of Cl2, what will be left over? Well, the first thing we have to figure out is which one is our limiting reagent. And based on this equation right here, we'd need a mole ratio between aluminum and chlorine of 1 to 1.5, but what we actually have is 1 mole of aluminum for every 1 mole of chlorine. So we have less chlorine than we need from our comparison of moles in our equation. So our chlorine is our limiting reagent. So we can calculate then how much aluminum is used up. We're going to take our 1 mole of chlorine, multiply it by our mole ratio between aluminum and chlorine, which in this case is 2 to 3. We're going to find that 0.67 moles of aluminum are used up. We're then going to take our starting amount of 1 mole of aluminum, subtract 0.67 moles that are used up, and we'll find that there's 0.33 moles of aluminum left over. It's fairly straightforward math, but it takes practice to get really good at it. Odds are you're going to mess up a few times before you get consistent at getting it right every time. Let's practice with a slightly more complicated problem here. So in this reaction, we have 3 MnO2s plus 4 aluminums reacting to give us 2 Al2O3s plus 3 manganeses. Right? So 17.5 grams of MnO2 are allowed to react with 9.8 grams of aluminum. How much Al2O3 will be produced and what will be left over? Again, we need to figure out which species is our limiting reactant. To do that, we're going to have to figure out how many moles of each is present. In this case, I've decided to figure out how many moles of aluminum would be used up if I used up all of my manganese, or my MnO2. So I take my 17.5 grams of MnO2 present, divide by my molecular weight of MnO2, and that tells me how many moles of MnO2 I get. Then I'm going to multiply by my mole ratio between aluminum and MnO2, which is 4 to 3, and and then I'll multiply by the molecular weight of aluminum to find that with 17.5 grams of MnO2, I can use up 7.25 grams of aluminum. This value, of course, is lower than my 9.8 grams of aluminum. You might ask, why did I choose to do it this way instead of calculating out how many moles of aluminum I produced or comparing the mole ratios, etc. And in this case, it doesn't really matter which of those four methods I used to figure out which one was my limiting reagent. But doing it this way, by figuring out how much aluminum is used up, it'll make it real easy for me to calculate how much is left over at the end. Okay, so we know that the MnO2 is our limiting reagent now because it will consume less aluminum than is present. So the next thing we need to do is calculate how much Al2O3 will be produced, because part of the question is how much Al2O3 will be produced. So we're going to take that 17.5 grams of MnO2, convert it into moles, multiply by our mole fraction, multiply by our molecular weight of Al2O3, and come up with 13.7 grams of Al2O3 being produced. Now we know how much is produced. Let's figure out what's left over. We started with 9.8 grams of aluminum. We used up 7.25 grams, so we're left over with 2.6 grams. So that's all there really is to it. If you have any questions about calculating leftovers, let me know. We don't have any fun names for leftovers. And some of you might say leftovers is a fun enough name, but we just call it leftovers. All right, now let's get into the last topic for today, and that is percent yield. So when we're mixing chemicals together to try and form a product, the amount of that product that we get out is often less than the amount we're expecting. So the amount we actually get out is called our actual yield. The amount we're expecting is called our theoretical yield. So then we need to figure out what our percent yield is by comparing those two numbers. And I'll explain that in a second. Now, the reason we usually don't get 100%, the most common reason is because oftentimes there's other side reactions, meaning that the chemical equation we have written out isn't the only chemical equation happening. There's other ones, sometimes we know about them, sometimes we don't, that are forming other products than what we're expecting. So if our starting materials are being used up to make other stuff, it's going to leave less starting materials to make the stuff we're trying to make. Sometimes the starting materials won't react completely, and sometimes you'll just mix them wrong. So there's a number of reasons why your percent yield won't be 100%. But now let's talk about really quickly how to calculate these. Again, your actual yield is how much you actually made. Your theoretical yield is how much you expected to make based off your amounts of starting materials and your chemical reaction and the stoichiometry involved. So your percent yield is calculated just by dividing your actual yield by your theoretical yield and multiplying by 100%. Okay, so for an example, if we do a gold extraction of ore and we were expecting to get 100.0 grams of gold out, but instead we got 91.2 grams of gold out, what is our percent yield? Well, the actual yield in this case is this 91.2 grams, and our theoretical yield was 100. So we're just going to take 91.2 divided by 100, multiply by 100% to find a 91.2% yield. It's a very straightforward equation. I always feel bad saying things like it's a straightforward equation because I know there's somebody out there thinking, I don't know that I can do that, but I think you can. Okay? All right, let's do a little practice. So let's say aluminum metal and liquid bromine react, producing aluminum bromide. In one experiment, 6 grams of aluminum reacted with an excess of bromine to yield 50.3 grams of aluminum bromide. Calculate the theoretical and percent yields. The first thing we're going to need to solve this problem is we're going to need to know the actual reaction and the stoichiometry involved. Okay, this is the reaction. we have 2 atoms of aluminum reacting with 3 molecules of Br2, and that's going to give us 2 units of aluminum bromide. Now we can calculate how much aluminum bromide we'd theoretically get. So let's read our question again. We're starting with 6 grams of aluminum and excess bromine, which means that our aluminum is our limiting reagent. So let's figure out how many moles of aluminum we have. So we'll divide 6 grams of aluminum by the molecular weight of aluminum, multiply by the mole fraction here between aluminum bromide and aluminum, which in this case is 2 to 2, and then multiply by the molecular weight of aluminum bromide, which is 266.7. From that calculation, we find that theoretically we should have made 59.3 grams of aluminum bromide, but that's not what we got. So this is our theoretical yield. Our actual yield was 50.3 grams. So then our percent yield, we're going to take our actual value of 50.3, divide by our theoretical value of 59.3, multiply by 100%, and find that we got 84.8% yield. One more practice. I hope you're looking at this practice and realizing that I could give you this equation, and I could say balance this, then calculate your molecular weights, and then calculate your percent yields. But in this problem, it's going to be a little bit simpler. Let's say when 884 grams of rust, or iron 203, was reduced with excess carbon. Reduced is another way of saying reacted. It's a specific type of reaction, but you'll learn about that in a little farther down the road. But 884 grams of iron 203 is reduced with excess carbon. 507 grams of iron were made. What was the percent yield? Well, how we're going to approach this problem is we're going to say that our iron 203 is our limiting reagent, because that's what the problem says. It says there's excess carbon. We're going to figure out how many moles there are of that by dividing by our mole rate, or our molecular weight of rust. Then we're going to figure out how many moles of iron should be produced by multiplying by the mole ratio between the iron and the iron 203, and then multiply by the molecular weight of iron, which is 55.845. And that tells us that we should have theoretically produced 618 grams of iron. But that's not how much we actually produced. We actually produced 507 grams of iron. So let's figure out our percent yield here. We're going to take our actual yield of 507, divide by our theoretical yield of 618, multiply by 100% to find that we got an 82% yield. Again, let us know if there's any problems there, if there's anything you don't understand. Now, some of you might be thinking to yourselves right now, well, how am I going to calculate the actual yield, or how do I figure that out if the problem is what is the actual yield? Well, you have to have some information about actual yield. It's not actually calculated from anything, it's measured. So the only really different way I could ask this question is if I started with 884 grams of iron 203 and I got an 82% yield of iron, what mass of iron was produced, or how many grams of iron were produced, or how many moles of iron were produced. So I could ask the question that way. So instead of giving you the actual amount of iron produced, I could give you the percent yield and ask you to calculate the actual. But beyond that, there's not much we can do to change that actual amount. We either have to give you the actual amount or the percent yield. Right, now, another question you might be wondering is if we got an 82% yield for iron, should we get the same percent yield for the carbon monoxide over here? And the answer is yes. So your percent yield should be exactly the same for everything you make. Now, that being said, oftentimes when we're measuring percent yields, they're not exactly the same. So we could say we got 82.0% for iron and 81.9% for the carbon monoxide. And the reason for that isn't because we didn't get the same percent yield, it's just that it can be hard to measure things. So first, if we have this reaction, we'll have to separate out these two species. But what happens if you have a little carbon monoxide dissolved in the solid iron here? Then that's going to make it seem like there's a little more iron and a little less carbon monoxide when in reality you got the same percent yield for both. So all of your products should get the same percent yield. That's not going to be affected by the coefficient in front of them. Their percent yield is independent of that coefficient. You do have to use that coefficient in calculating the theoretical yield, but percent yield is independent of the coefficient. All right, let's bring that all together into one problem. Let's say we start with 50 grams of iron 203 or rust, and we start with 50 grams of aluminum, and they're mixed together and ignited in a thermite reaction. And after that thermite reaction, 33 grams of iron were produced. Let's figure out what was our limiting reactant and what was our percent yield. Okay, so the first thing we're going to do is figure out how many moles of rust were present, how many moles of aluminum are present here. Okay, and as you can see, there are 0.313 moles of rust present, and there are 1.853 moles of aluminum. Looking at our equation up here, we should have 2 moles of aluminum for every 1 mole of iron 203. But down here, 1.8 compared to 0.3, 1.8 is about 6 times greater than 0.3. That means is we have a lot of extra aluminum. So our aluminum is going to be excess. Our iron 203 will be our limiting reagent. So we'll use our 0.313 here to figure out how much aluminum is used up, and we'll do that by multiplying by our mole fraction here of 2 moles of aluminum for every 1 mole of iron 203. Find that we used 0.626 moles of aluminum. That'll help us figure out how many moles of aluminum are left over. We'll just take that 1.853 moles we started with, subtract the 0.626 moles we used. Now we're left with 1.23 moles of aluminum left over. And that's assuming that everything reacts completely. Okay, next thing, let's figure out how much Al2O3, how much iron we should have produced from that reaction. And we will find that when we take our 0.626 moles of aluminum that are used up, multiply that by the mole fraction between aluminum and iron, which in this case is 2 to 2, and then multiply by the molecular weight of iron, we should have produced 34.96 grams of iron in that reaction. So from this is our theoretical yield. We have an actual yield of 33 grams. So we can calculate our percent yield by taking our actual divided by our theoretical times 100% to get us 94.4% yield. All right, some of you might be wondering then, if our iron 203 was our limiting reagent, why did I calculate the theoretical yield from the amount of aluminum used up? Well, the simple answer for that is it doesn't actually matter whether I use the amount of aluminum used up or the amount of iron 203 used up. You should get the same theoretical yield for iron. So a good way to check your theoretical yield is actually to calculate it using both. Using your limiting reagent, and then using your limiting reagent to calculate how much of your excess reagent is used up, figure out, and then use your excess reagent used up to figure out your theoretical yield, and use your limiting reagent to figure out your theoretical yield, and they should be exactly the same. Now, some of you might be thinking, well, there's 0.313 moles of iron 203, and there's 0.626 moles of aluminum, so how's your theoretical yield going to be the same if you're starting with different moles of the different reactants? Well, the reason that they're going to be the same is because they have different mole fractions. So not only do they start with different numbers of moles, but they have different mole fractions, and that mole fraction is going to change them each to give this value out at the end. So that is limiting reagents, percent yields, and a little bit of leftovers. Hopefully that was helpful to you. let me or the TAs know if you have any questions or concerns.